Welcome to video 18 on the TTB course. This video is from part 4 of the course. In part 4 we consider techniques for monitoring TT systems. In this video we consider techniques for monitoring task execution times in a TT system. The material in this video is based on chapter 18 in the ERES2 book. If you have not yet read chapter 18, I suggest you stop the video now, read the book chapter and run the video again. A key reason for choosing a TT architecture is that we are able to model system characteristics such as the maximum CPU load, the task release jitter and the response times. One of the main assumptions upon which such a model is based is that we know the worst case execution times and best case execution times of all tasks on each processor in the system. At runtime, we need to ensure that the task execution times lie between these lower and upper limits, or our models may not be valid, our platform may not operate in accordance with the system requirements. This is the task list that we expect to see, and this is the task sequence that we expect to see. If in fact what we see is something like this, so in this scenario task A has overrun, then by the time task B runs and the scheduler ISR is called again, then tick count G will exceed the tick count limit because we have not yet completed the release of all of the tasks in the set. So we have a simple mechanism here that will result in the system being forced into a safe shutdown state as a result of the overrun of task A. However, this mechanism is really rather basic and rather crude. When we actually detect the overrun, we detect the overrun when task B is executing. And it would be difficult at this point, if we wish to do so, it would be difficult at this point to identify the particular cause of the detection of the problem when task B is running. It's difficult to tell whether task B has suffered from a problem or task A has suffered from a problem, for example. To provide much more precise control of execution time monitoring, we use a monitor unit. We'll describe how to use a monitor unit in this video. So this is an overview of the behavior that we would expect in a monitor unit. We're focusing again in this example on task A. The task set is the same as the one we've looked at in the previous slides in this video. So before we release task A, we're starting a timer. If task A doesn't complete within its worst case execution time, which is illustrated in this figure, then the monitor ISR will be triggered. So we start a timer and we associate that timer with an ISR, and we set the timeout value for this timer to be a little greater than the worst case execution time of task A. So if the task does not complete, if the task completes correctly, then we have a stop function that's part of the monitor operation that's called when the task completes. That function will disable the timer and will stop the triggering of the monitor ISR. The stop function here will also be used to check that the task has not completed too quickly. That is, the stop function will also be used to check that the task has not breached its best case execution time limit. Overall, this is a very simple mechanism, but in this expanded graph you can see here that we can pick up, for example, the overrun of task A in this case very quickly in comparison with the simple method that we've used so far. In this case we're picking up the overrun of task A in something a little under 1 tick, whereas previously, using the simple mechanism we used before, we would have had to wait until we got to the next tick before we could detect an overrun. So we can get very precise monitoring of the task execution time using this simple monitoring approach. So this is an indication, an illustration of a situation in which the monitor unit is used and task A in our example exceeds its predetermined worst case execution time limit. So in this case the monitor ISR is called and we assume the system is forced to shut down. Of course, there are different approaches to handling this situation. You might decide, for example, that a same mode reset is appropriate, that switching into a limp home mode. There are numerous other possibilities. The simplest solution is to force the system into a fail-safe state in the event of this overrun, and that's what we're assuming in this example. This example illustrates an underrun situation. So we're assuming that task A has completed and that when we've checked the execution time based on the monitor timer when the task completes, we decide that the task is completed in a time that's less than its best case execution time limit. In these circumstances, we may also decide to take action. This action may include shutting down the system, placing the system into a fail-safe state. This is a code example. This one's for an LPC 1769 processor. This is taken from the first edition of the ERES book. You'll find all of the code on our website, and you'll find some later examples of monitor implementations in the ERES2 book. So in this example, all we're doing, the code is very simple. So we're starting the monitor process just before we release a task. And we're storing information about the task, worst case execution time, best case execution time, and we're allowing a degree of timing variation in the task. So we might allow the task to overrun or underrun by, say, 10 microseconds before we take any action. And that's what this parameter allows us to do. So we set the timer here, timer 0 in this case, to the allowed timeout value. We complete the timer configuration and we enable the interrupt for timer 0. It's a very short process. This is the monitor ISR itself. So all we're doing here is checking and clearing the ISR flag, and in this case all we do is we force the system into a fail-safe state, and we store the fault code, which in this case we're assuming is a task timing fault. We're not storing the task ID, and we're not distinguishing between best case execution time and worst case execution time errors, but we can do both of these things if we need to do so in a particular implementation. This is the stop function, which is used to check, which is called every time a task completes to determine whether the task is completed too quickly and whether we have an underrun situation. So we stop the timer, we read the execution time, and then we check whether the execution time is less than the best case execution time limit, allowing for the timing variation. If the task is completed too quickly, then using this particular implementation framework, we force a shutdown. Again, we're not storing the task ID, and we're not distinguishing between best case and worst case errors. And again, both such checks can be carried out if required. An important consideration with any form of monitoring system in a safety-related or high-reliability system is that we need to consider how we will perform power-on self-tests and built-in self-tests of the monitoring components themselves. So during power-on self-tests, we would expect to check the monitor unit by applying both a task underrun and a task overrun scenario. We would probably also expect to perform further periodic tests of the monitor unit during the platform operation in the majority of cases. We'll assume that as with the internal watchdog timer, any such built-in self-tests will be carried out by means of a same mode reset, unless another solution is found to be a better match for a particular platform. So our default would be to carry out tests of the monitor unit periodically by means of a same mode reset, unless we wish to use an alternative solution. We've talked previously about some appropriate diagnostic test interval values. Again, the values in this table can be used as the beginnings of a discussion about this matter. So the DTI values, the diagnostic test interval values, will vary depending on the particular platform that is employed. And we'll say more about these platforms in video 21. It's important to appreciate that the monitor units presented in this video and in Chapter 18 of the ERES2 book may not operate as expected when used in designs like that shown below. So in this design, we're assuming this is correct behavior for the system, in that we're allowing task B to be released in tick 0 and to complete in tick 1, and we assume that that is correct behavior. If we use the standard monitoring unit with this type of design, then the overhead from the scheduler ISR may be enough to cause the task to exceed its expected worst-case execution time limit. We present some designs in the ERES2 book in Appendix 10 that can be used to monitor execution time in systems where one or more tasks complete after a tick. You might like to take a look at Appendix 10 for some information about such monitoring systems. We are gradually beginning to assemble a range of different monitoring options for the different platforms that we're looking at on this course. If we start on the left in this slide, a correlator A platform that we'll look at in more detail in video 21 is a simple TT platform with no external monitoring. This is likely to include an internal monitoring unit implemented on MCU-A. A correlator B platform will also include an internal monitoring unit, and it will also have an external watchdog controller of the type that we discussed in a previous video. The correlator C platform may include an external monitor. So the correlator C platform includes a second microcontroller implementing what we call a warrantor unit. This warrantor unit may include an E monitor, an external monitor unit that is used to check the execution times of the tasks on MCU-A. We'll say more about the correlator C design in video 21. That brings us to the end of this video. Please read Chapter 19 in the ERES2 book before you continue with the course. Thank you for watching.